In the last lesson, we looked at compound angle formulas, and you can see them all right here. Today we're going to look at some specifics of compound angle formulas, as in what do we do if we have two of the same angle, and we call those double angle formulas. We're also going to do an application using compound angle formulas. So let's jump right in. So double angle formulas, as I said, are if A and B are the same. And when I say A and B, I mean A and B in whichever formula we're looking at. All of them involve two angles because we're breaking things down into two angles. And so if A and B are the same, really it's just two of the same things. It's a double angle. It's double whatever the angle is. So let's develop these for sine and cos. So let's just call the angle theta. So if we were to call angle A theta, actually let's say angle A equals angle B, which equals theta. So angle A and B are the same, and we're just going to call it theta to keep things simple. And then sine 2 theta could be thought of as sine theta plus theta. Theta plus theta is 2 theta, of course. And then if we go back and look at our sine addition double angle or compound angle formula, we can see that it looks like what I've just highlighted. So replacing A and B with theta, I get sine theta sine theta cos theta plus cos theta sine theta. There we go. And then we can simplify that. It doesn't matter which angle or which order they go in. I shouldn't have written that all on the same line, though. That's a bit sloppy. Let's move this down here. That's a bit better. And but sine theta cos theta is the same as cos theta sine theta. So really I've just got two of the same things. So that's equal to 2 times sine theta cos theta. And that's the first of our double angle formulas. In fact, let's just say sine 2 theta, and then that equals 2 sine theta cos theta. Let's do the same thing for cos 2 theta. So if we go back and look at cosine now, we have cos A cos B minus sine A sine B. So this is going to be, again, the same as cos theta plus theta, but that's cos theta times cos theta, since A and B are both theta, minus sine theta times sine theta. Cos theta times cos theta is just cos squared theta. Likewise, sine theta times sine theta is sine squared theta. So here we have another one of our double angles. Turns out for the cos 2 theta double angle formula, we can actually rearrange it and come up with a couple other versions of it. Think back to trig identities. You should have learned, hopefully in the past, something called the Pythagorean identity, which says that sine squared theta plus cos squared theta equals 1. That can be rearranged. It could be rewritten as cos squared theta equals 1 minus sine squared theta. So in other words, if I just bring the sine squared theta to the other side of the equation. It could also be arranged, if I want to isolate the sine squared theta, as 1 minus cos squared theta. So both of these are equivalent to the original Pythagorean identity. But if we then take this and substitute it into the double angle formula we just had, so again, if we go to cos 2 theta is equal to cos squared theta minus sine squared theta, if I take 1 minus sine squared theta and put it in for cos squared theta as a replacement, as a substitution, I'd get 1 minus sine squared theta minus sine squared theta, which is already there. So the blue is just to show that where things came from, but then I could simplify, because minus sine squared theta minus another sine squared theta is just the same as 1 minus 2 sine squared theta. And that would be a second version of the cosine double angle formula. And the last one's going to come from substituting sine squared theta, or 1 minus cos squared theta in for sine squared theta. So again, cos 2 theta is equal to, and again we're starting with cos squared theta minus sine squared theta, but we're going to replace the sine squared theta with 1 minus cos squared theta, like that. Now, because of the double signs going on here, the double negatives, we end up with cos squared theta minus 1 plus cos squared theta. So if I rearrange that and gather up my like terms, I get 2 cos squared theta minus 1 would be the most simplified version of this. And that's supposed to be a squared there. All right, so that's our third version of a double angle formula for cos 2 theta. As far as tangent goes, then again we can think of this as tan theta plus theta. And that means if we go back to this formula up here, we're going to use this version, tan A plus tan B over 1 minus tan A tan B. But now we have tan theta plus tan theta over 1 minus tan theta times tan theta. Tan theta plus tan theta is 2 tan theta. Tan theta times tan theta is tan squared theta. And there's our formula for tan 2 theta. So every one of these 5 formulas we just developed just came from taking double angle formulas and rearranging them. So let's use it. Express each as a single trigonometric ratio. So what we're supposed to do in this question is look at this and go, oh, wait a minute. That looks kind of like something I've already seen. Cos squared something minus sine squared something. Where did I see that? Oh, there it is. Cos squared theta minus sine squared theta. If I work that backwards, that's the same as cos 2 theta. So I just got to find out what theta is, double it, and it'll be equal to cos 2 that. So if theta in this case is 3 theta, I know it's confusing to replace theta with 3 theta, but basically our angle is 3 theta. So our double angle formula says that I can rewrite that as cos 2 times, and then whatever the angle is, which is 3 theta, highlight it. And so that's the same as if I did the cos of 6 theta. So if I did whatever theta is, if I did cos squared 3 times theta minus sine squared 3 times theta, I could get the same answer if I did just straight cosine of 6 times theta. I'd consider that simplified. Likewise, I need to identify what my angle is in B part, because that looks like our double angle formula for tan, and our angle would just be 5x. So I recognize it as double angle formula for tan, so it would be tan 2, because that's part of the double angle formula, the angle, which in this case is 5x. So that simplifies down to simply tan 10x. Here's some where we can simplify and then evaluate. If we look at A part, 2 times the sine of pi over 6 times the cos of pi over 6. We can do this. We have special triangles for pi over 6, so we could certainly figure that out. But we could also use the double angle formulas to help us simplify it first and make it a bit easier, because you may recognize that this is actually just the sine double angle formula. I went too far. There it is. Sine 2 theta times cos 2. Sine 2 theta equals 2 sine theta times cos theta. And that's really what we've got here, so that theta is pi over 6. So again, I can work it backwards. I recognize it as sine 2 times the angle, which is pi over 6. Simplify it. 2 times pi over 6 becomes 2 pi over 6, which is just pi over 3. And if I use my special triangle, let's draw it like this. Remember, the pi over 3 triangle went 1 to root 3, so I want the sine, which would be opposite over hypotenuse, so it's just going to be root 3 over 2. Again, if I look at this, this is one of my double angle formulas, one of my versions for cosine. So my angle is pi over 12, but I recognize that this is going to be the same as the double angle for cosine, so cos 2 times my angle, which is pi over 12. 2 times pi over 12 is 2 pi over 12, but that reduces to pi over 6. I can use this same special triangle that I've drawn over here to help me, because inside the same triangle is pi over 6. And now from this angle here, I need to take the adjacent side and the hypotenuse. So adjacent to pi over 6 is the root 3 again, the hypotenuse is root 2 again, so it turns out that once again we get root 3 over 2, but just for slightly different reasons. Now the last example we're going to look at isn't a double angle. It's back to just using compound angle formulas, but it's just, a little something different once again. Angles x and y are located in the first quadrant such that sine x equals 4 over 5, cos y equals 12 over 13. The fact that they're in the first quadrant does matter. We want to find various things. Like we want to find an exact value for cos x. Okay? Well, let's draw a picture. When in doubt, draw a picture. Well, let's use a blue pen, not a highlighter. So in the first quadrant, we've got this sine value of 4 over 5. So remember, all the trig ratios are related to different sides of the triangle. So sine is opposite over hypotenuse. So I know I have an angle that's going to have an opposite side, of 4 and a hypotenuse of 5. So maybe the angle looks like this, or the terminal arm looks like this. That way, when I draw my triangle here in the first quadrant, opposite is 4, hypotenuse is 5, I got to find an exact value for cos x, because I know that sine x equals 4 over 5. So in order to know what cos x is, I need to know what that side is there. Well, that's just a 3, 4, 5 triangle using Pythagorean theorem. You might recognize it, but if you don't recognize it, then you might know that, let's call this m. We know that m squared plus 4 squared equals 5 squared, because 5 is the hypotenuse. So m squared is going to equal, well, m squared plus 16 is going to equal 25. So m squared is going to equal 25 minus 16, which is 9. if I take the square root of each side, m equals 3. So as I said, that's a 3, 4, 5 triangle, classic. But then if I want to find a value for cos x is going to equal adjacent over hypotenuse. So it's going to be 3 over 5. Determine an exact value for sine y. Okay, same thing. This time it's still in quadrant 1. And we know that cos y is 12 over 13. So that's going to be a very steep line because the hypotenuse and the opposite side are almost the same. Sorry, my bad. I was thinking that was sine. It's actually the opposite. It's a very not steep line because the adjacent and the hypotenuse are almost the same. So it's more like this. So we get 12 as my adjacent side, 13 as the hypotenuse. And now I need to find out what the opposite side is. So let's call it n. Again, we can just use our Pythagorean theorem. So n squared plus 12 squared equals 13 squared. So n squared is going to equal 169 minus 144 once we expand them out. So that's going to equal 25. And when I take the square root, n equals 5. You may have known that one as well. So here's 5. And that means that I can then get my value for sine y by doing opposite over hypotenuse, 5 over 13. Okay, so far I've got 4 trig ratios. I know what sine x is. I know what cos of x is. I know what cos of y is, and I know what sine of y is. Why might I want all of those? Well, because now I can determine an exact value for the sine or cos or tan, if I wanted to, for adding or subtracting angles x and y together. In this case, part C asks us to add them together. So this is a compound angle. And if we go back, remember sine x plus y, this is going to be the same as sine A plus B. So it's sine A cos B plus cos A sine B. So it's going to equal sine x cos y plus cos x sine y. Okay? Again, what are sine x and cos y and so on? Well, that's what we just figured out. Sine x is what I highlighted in yellow. It's 4 over 5. And cos y is what I highlighted in green. It's 12 over 13. In fact, why don't I even highlight these again? Yellow, green, blue, purple, not blue and purple. Sorry, no, it was purple and orange. Purple, orange. So what I highlighted in purple is my cos x, which turned out to be 3 over 5. And what I highlighted in orange is my 5 over 13 sine y. Now I just have to combine these fractions so I can follow order of operations and multiply. I get 48 over 65 plus 15 over 65. Add, because I've got common denominators, and I get 63 over 65. And that can't be reduced anymore, so that would be my answer for C part. Now there's no questions at the bottom of this page. I believe that they're back on part 1. Just find that. So part 1, I think the double angle questions were also here on part 1. Yeah. So you have to go back to the previous day's note, previous lesson's note, in order to get the practice